Hello, everyone. Just wanted to go over the article I just published on my blog, niledataHub.com. And this is about a deployment of actual machine learning models on the factory floor, and how a machine learning models that you might have built on the cloud, where you have powerful GPUs and almost unlimited resources, could fail when we deploy them on the edge, basically. So I start by talking about this illusion of having the perfect accuracy in the lab. Um, but when we deploy the model in the real world, this accuracy could drastically change, or the model could basically fail under the constrained operating conditions of the lab and the hardware under the constrained conditions of the real world, and the models could potentially fail due to the lack of resources, memory, and processing powers. But why do we want to deploy on the edge on such a restricted resource system? The reason is a combination of latency, privacy, reliability, and availability. So let's say you're monitoring some manufacturing process like a production line in real time, and you want to get a quick answer, something in the order of 5 to 10 milliseconds, and you have, let's say, a video camera system monitoring a production line and looking for potential defects in the process. You don't want to rely on your connectivity to the cloud, and the sheer amount of time you have to wait for the round trip might not be enough or sufficient to support the current production process. There's also concerns about the privacy, and manufacturers and factories, they don't want to share samples of their production lines or the components or equipment, so they don't want to upload these images or these videos to the cloud. There is also security and reliability of the connection, and also the availability of the cloud is down, then basically you can't monitor your production line. So we want to make sure we're always as close as possible to the equipment that we're monitoring. We're not relying on a connection, and we're avoiding the two-way trip timing to get a prediction. So these are some of the concerns that basically dictate the use of edge AI in factories and workshops and shop floors. And the reality is we could have a combination of edge computing devices or industrial PCs or embedded systems. And these systems, as I said, are very limited in resources. So how can we take that model that we developed in the lab and then put it into production in the real world? That's what this article is trying to address. And this missing layer is, how do we translate from this model that we built on the cloud to the real world, where we could have different types of a hardware, like a GPU that could be, NVIDIA or non-NVIDIA and GPUs, could be neural processing unit or a digital signal processing PC that's optimized for dealing with signals, images, and sensors. So in this article, I don't go into the whole process of optimizing architecture from a fundamental standpoint, which is, and I'm giving some example for some of these networks like efficient net, squeeze nets, mobile net, and all of that. I'm just assuming we have some architecture, and let's say it's optimized. Hopefully, it's optimized. And then what can we do in a practical sense to optimize the architecture further and to deploy it on a constrained device? So I divide this into two types of optimizations. The first one is high level optimizations, which you can do in Python using any of the frameworks like PyTorch or Keras, TensorFlow. Um, and I explained three of these. The common ones are pruning, which is a process by which we're pruning connections and pruning neurons that are not contributing significantly to the prediction of the network. So we're going to add the loss functions, and there's different ways to go about this. There's heuristic methods, which are easier and more convenient and faster and efficient compared to other more formal methods, such as taking the Hessian of the loss with respect to the weights and trying to minimize that. The heuristic usually work best, which is looking at coefficients or weights that have small magnitudes, or neurons that are connected to a bunch of weights whose variability is very small. And the variability being small means they do not contain information or significant information content. So these are the ones that are safer to eliminate. Uh, but once we do the pruning, our job is not done. We still have to do retraining to or fine tuning of the models that have been pruned in order to retain the previous performance. So I'm showing here in this graph, for example, a network that has been pruned with training and without retraining. Um, so as you can see, the bottom curve is with retraining, and we're able to take the parameters from almost 3,000 all the way to about 700. It's a huge reduction in the number of parameters compared to the original size. But if we're doing the pruning without tree training, we start to lose performance as the number of parameters is drastically reduced. The second approach to compression of the networks is quantizations. And this is not just a specific to neural networks, but it's actually for any analog to digital conversion system that takes the weights or the quantity of the signal we're interested in quantizing and dividing it into subranges, as you can tell from the graphs. And you can do this in a uniform fashion. As you can see, the step sizes are the step width is basically about the same across all the range of weights, and you can do this. You can do this in a more non-uniform way using different algorithms such as Huffman encoding, where we're focusing basically on designing this nonlinear mapping between weights and digitized values, such that values that occur very frequently take small number of binary bits, whereas rare values take much more representation, and that's what makes it very efficient in compression. So the third approach is knowledge distillation, and this is like the teacher-student model, and the student is the small, lightweight architecture compared to the teacher. The teacher is a more comprehensive, um, a more complex model, and we use the prediction from the teacher to train the student model. Um, but we're doing this in a very careful manner. We're not just looking at the prediction from the network where the zeros and ones. Let's say I have a classifier a, that gives me dog, cat, and boat, for example. I'm taking the prediction, the probabilities, or the logits from the teacher model, and I'm feeding this as the ground truth for the student model that basically allows it to learn not just the hardcore or the hard targets, but the soft probabilities that allows the model to understand the relationship or the similarities between the different values, like the dog and the cat, versus other non-animal objects that we're trying to classify, like a boat, for example. So that is also additional layer of optimization that can work in the real world that allows us to deploy very efficient models that learn from more complex models. So this is the first layer, which is I would say, hardware agnostic. But there is the additional layer of a hardware level optimization that is very specific to the hardware that on which you're deploying your models. So we use something like TensorFlow Lite, which has been rebranded as Lite-RT by Google recently, that allows us to do a lot of optimization for your network, and basically allows us to transform the model into something that the hardware can understand, or a lot of the edge devices can understand. It's efficient, but also it's understandable by these devices. We also use libraries such as ONNX that allows us to move between frameworks. So if you develop something in TensorFlow or PyTorch, that ONNX basically allows us to um, distill the graph of the or transform the graph that has been built by these frameworks into some uniform, universal representation for these graphs that hardware accelerators on the individual hardwares can understand and can deal with. So we have these basically, or this decision matrix that allows us to start from from a deployment target all the way to the actual hardware that does the computation, the essentially matrix multiplications that occur at the very core, that are the very core of a machine learning models. So depending on the hardware, for example, NVIDIA, we can basically export through our NNX to a uniform representation. And from there, using TensorRT, we can basically optimize the calculations for deployment on NVIDIA GPUs. We could also have another case where we have industrial PC, and we're also using ONNX to um, basically have a representation that OpenVINO can use to optimize the calculations on the hardware. And another branch for the mobile apps, we can use TF Lite, and from TF Lite, we can use NN API to optimize the calculations on these mobile devices. So it's very clear that it's an alignment problem, or alignment of the model in the runtime and the hardware. If some of if these components are not aligned, then the models can potentially easily fail in the real world. So these are some final thoughts. I summarized the article, and I emphasize the importance of compatibility between the models, the runtime, and the hardware execution in order to have something successful in the real world on that operate on reliably on the factory floor. Thank you.